So for this geometry final review, you may have already seen part one. So if you already know what to do, then go ahead and skip to whatever questions that you want to review. If you haven't and you just happen to come across this one, take the exam. The link is in the description. And then once you've taken that exam, go ahead and check your answers. And whatever ones that you've gotten wrong, you go ahead and look at the description. I put timestamps next to each question, whether it's in this part or any of the other two parts. Make sure you go over the missed ones. I go in depth on the actual question itself. And then next to each of those questions in the description, I'll put a link to some extra practice problems so that you can get a little bit more practice in case you want to make sure that you're comfortable with whatever the topic might be. So that's pretty much how these ones go. So let's go ahead and get started. All right, so we get a couple of shapes here, and it looks like they're asking us what sequence of rigid motions maps this shape onto this shape. Rigid just means that the shape is not going to change size or any of the angles are going to change or anything like that. And when it says maps onto this, it means that when we move this, it literally kind of turns into this by the time we're done moving it. Okay. So you could take a look and say, all right, now a lot of people are going to be tricked by this and go from here to here. Remember, if they're saying, if we're mapping this onto this, that's where we're starting from, and then we want to go from there. And there's multiple ways that we could do this, but there's only one, hopefully, that's right here because there's one right answer. So if we take a look, if I rotated this 90 degrees counterclockwise, I want you to imagine this A. We're just going to stick with one point. If it's 90 degrees counterclockwise, what that's going to look like is it's roughly going to be right here now. You can imagine these two lines that I drew create a 90-degree angle. So now A is going to be right here, -2, +2. Okay. Now, if you take that and say, all right, well, now let's reflect that over the x-axis. Okay, so if I reflect this over the x-axis, it's going to go, it's 2 above, and then it's going to be 2 below. A would be right here, but that's not what we get. We get E double prime. Okay, so that's right off the bat. That's not it. But you can imagine we're getting pretty close because if I do rotate rotate 90 degrees counterclockwise, A would be right here. And if you take a look, how far do I have to go down to get to A double prime? 1, 2, 3, 4, 5, 6, 7. We'd have to go 7 down, right? So that's why we would do a rotation 90 degrees counterclockwise, and then we would translate it, literally just move it. Imagine moving your hand across a sheet of paper. That's a translation down 7 units. That's what we're doing here, okay? Really kind of tempting to say, all right, well, let's reflect it over the y-axis and then reflect over the x-axis. But if you can imagine we did that, it would look like, pardon my drawing, and then if we would reflect it over the x-axis, it would look like this instead. So it can't be 3. And I want you to kind of imagine doing the same thing for number 4. We reflect over the x-axis, we're down here, and then we rotate it counterclockwise 90 degrees. If we did that, however, it would end up with the same shape, but E would be down here. Well, in this case, E double prime. Okay. And again, pardon my drawing, but that's all we're doing for this one. All right. If you're not comfortable, the translations are pretty straightforward. You literally move it up, down, left, right, however many units. But the rotations are, for me, they were always the hardest because it was like, what does it look like if I rotate it? There are rotation rules where it's like, oh, if it's 90 degrees, X and Y become blank. If it's 270, it's blank. So make sure you memorize those. It helps a lot. But sometimes you can kind of eyeball it and look and be like, okay, well, looks like it'd be like right over here. And the straight line that you draw from the origin, because we're going through the origin in all these problems, the rotation, the 2 lines that you draw from the original to the new, what's called the image, should make 90 degrees, whatever your angle measure is. Okay. Now, again, that's not perfect. I would much rather you remember the rules, the rotation rules, because that just makes it much easier. And then you can double check your answer when you do eyeball it and be like, oh, okay, yeah, it does follow that rule. It's not very fun, but I promise you, if you can remember those rules, it makes life a lot easier when you're rotating shapes. As fun as that is. So that's all we're doing for this one. The answer would be number 2. So for number 18, they give us a rhombus and they give us the vertices, and basically they're just asking us what is the area of the rhombus. All right. Now there's 2 ways you can do this: the hard way and the easy way. I'm going to show you the easy way because you do need to know the formula, but then I'll show you what the hard way would be if you didn't know this formula. So luckily for the rhombus, there's actually a really nice formula to find the area, and I'll write it right here. It's, well, we could use lowercase, d1 times d2 divided by 2, where d1 is the diagonal, the first diagonal, d2 is the second diagonal, and you divide it by 2. That's the area of a rhombus. Now you could, there's the harder one in this case would be the height times, you could call, I mean, there's multiple ways we can call this, times the length if you want. But we don't know the height. A lot of people will use, this length right here as the height, but it's this height. It's, imagine like a square. It would be that height where this line creates a 90-degree angle. That's the actual height. It's not the diagonals that are the height. And then you can multiply by, one of these, okay? But we don't know the height. To find the height, we'd have to do, this is the harder part, I say we have to find, imagine we have a right triangle now. We'd have to find this length by using this, and using this length down here and doing the Pythagorean theorem. We don't want to do that. You could, I do want you to know you could do that, but I don't want you to do that because there's the easy formula. Because it just so happens that it's really easy to find the diagonals in this case. Because they're all, this one's horizontally, a horizontal line. If you take a look, what's that distance from A to C? That looks like a distance of 6. So we'll put, 6 right here. And then the distance from D to B, that looks like a distance of 8. So the whole distance is 8. So we know what these are. We know D1, we know D2. We just plug in the formula. 8 times 6, all divided by 2. And we get, there's a couple ways you can do this. I like to just simplify these. 4 times 6, that's 24. But if you just do this, 48 divided by 2, we still get 24. Okay, that's the formula I want you to remember for a rhombus. Multiply the I can't even talk. Multiply the diagonals together, divide by 2. If you don't remember that formula, you can still get it using, but you have to find the height of the rhombus first, and that would involve the Pythagorean theorem. Not very fun, but you can do it. All right, so I didn't want you to know that, but this is where we want to go with that one. Okay. All right, our favorite type of problem, ones that have multiple possibilities. So basically we're looking and seeing, all right, which one, if we create a two-dimensional cross-section, so if we cut through it two-dimensionally, would have that as a triangle, that particular section that we cut out. All right, so if you've ever seen this channel before, you know that I'm not a very good drawer, so I went to the internet to find these shapes. So we'll go piece by piece, all right? If we look at a cone, there's multiple ways you can cut any of these shapes, all right? But we're just looking for one. That's all we care about. Can we get one triangle if I cut through this? And I want you to be able to look at this one head on, all right? If I cut straight down, imagine it's like taking a, cheese grater, I can't think of a word, and just cutting straight vertically down. Look at what the shape would be if we kind of took it out. It would look just like that, roughly. But that's exactly what it would be. That would be a two-dimensional cross-section that is a triangle if we cut straight down on a cone. All right, so that's, boom, right there. We're done with that. We know that a cone is one that has a triangle as a two-dimensional cross-section. So we know it can't be 1 because it's not just, no, sorry, not 1. We know it's not just 2 because we know 1 has to be an answer. All right, so let's go to a cylinder. If you take a look at a cylinder, it doesn't matter if I cut it horizontally, like straight through horizontally, what I would get is a circle. Straight through vertically, what that would, and it's not very obvious, but what that would give me is a rectangle. And depending on the size, it could give me a square as well. If I cut through it diagonally, that's going to get, what would that be? I think something like this. Roughly, kind of like that, parabola. You'll learn about those in pre-calc. That'll be fun. But there's no way that we can cut through this and get a nice triangle, okay? But if you look, and there's a shortcut I'll show you at the end to go through this, but we know it can't be 2, all right? So anything that has a 2 in it can't be that. And now, if we can just find out one more, our only choices are 1 and 4. If we can get 3 or 4 to be a possible solution, then we know, what the answer is. So let's take a look at a square pyramid. If you look, it looks very similar to a cone, all right? They just, the bases are different. That's literally kind of the difference between these. So if I cut vertically on this one, I want you to imagine, look what would happen. If I cut vertically through this, we see the face already of that as a triangle. But again, if I cut straight down on it vertically with a cheese grater, what I would get out, if I slid out the piece that I cut, that would look like that, roughly-ish. But that's what we would get. If we cut down vertically, we would get a triangle. If I cut through horizontally, I would get a square. Okay, but we get a triangle with that. All right, so it can be a square pyramid. 4 is an option. All right, so we know that it can't just be 1, so we know 3 has to be a choice, but I want to show you, with the cube what that would be, because again, if I cut vertically or horizontally straight through, I'm going to get a square back. But if I cut like this, if I cut it diagonally through the corner in such a way that the cutting is done to where the legs right here, not the legs maybe, but the sides are bigger than this base right here, then what I would get is whatever the size is, like that. Okay? So that's what that would be if we cut through vertically. No, not vertically, diagonally through a corner, if you want to call it that. That's actually probably the best way to describe it. So here's the shortcut around that. Obviously, I never liked these problems. I was not very good spatially. But when we're doing that, if they're asking for a triangle, right? Well, a triangle has a point, has multiple points, but it has a point. If you look at this one, there's no points on that. There's no way that we can cut through and get to a point. So there needs to be a point on whatever we cut through. And if you notice, point, 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 all those have points. All right. So keep an eye out for that. Now that only goes for if we're looking for a triangle. Okay. If they're looking for a rectangle, completely different story. In which case all these could be an answer except for the square. But that's pretty much it for that one. And again, you don't have to memorize that last shortcut part, but I do want you to see the similarities, the relationship between the ones that did work and the one that didn't work. There's no points on this guy. All right. So that's what we want to look for these. But again, if you can just kind of mentally, that's what you really have to do. You can memorize these all you want, but you have to be comfortable mentally going through and kind of like pretending you're slicing through vertically. What would that look like? Or slicing through horizontally. What would that look like? Based on the shape of the base, look at the shapes of the bases or the faces, whatever that is. That's how you kind of get through these types of problems. All right. So everything except for a cylinder. So that would be 4. And that's what we do for that one. So before we get started on this one, what I need y'all to remember is how to write the equation of a circle in general. So as fun as this looks, this is and you can kind of look how it looks exactly like all these. This is the equation of a circle down here. I think it's the standard form, if I'm not mistaken. Standard and general. General, I think, is different. This guy is the standard form of a circle, if I'm not mistaken. I could be wrong. But H and K right here, I should have written this out already. HK is the center of your circle. And R is the radius. All right. So what they tell us already is that, okay, well, what's the equation of a circle whose center is at 2, -4? So if I plug it in down here for H, we already know what HK is. It's 2, -4, right? 2, -4. If I plug it into this formula, I get x minus 2, y minus -4. That's everybody's going to get tripped up on the double negatives. I did. Everybody I know did. It just happens. So be careful about that. There's already a negative in the formula. So if you get a negative coordinate, it's going to turn positive. So we know that the left side of our equation is going to be x minus 2. So automatically we can get rid of 3 and 4. Nope. And then we can say y minus negative. So y plus 4. Okay. And obviously that would make sense that they're both the same here because we need to find the radius. That's where this part comes in, and I've seen a lot of students get confused about this because it's confusing. So if we take a look, that's why I put this here so we can actually graph it. You don't have to do this. I would highly recommend maybe on scratch paper, draw like a little, a half kind of, something along the lines of an axis so you know what's going on. But basically, here's our circle. We know it's tangent. When they mean by tangent, you probably know that word. If it's tangent to a particular blank, whatever, shape, a line, it just touches at one point. That's super important to know. I'm going to draw this line here. X equals -2. That is a vertical line at -2. So that looks roughly like that. And so we know that our circle is tangent to it. So if I draw it, imagine me drawing the circle and it barely touches. Well, okay, let's try that again. Barely touch it. Okay, pretend it just barely touches right there. Barely touches at -2, right? And then so if I continue to draw this, what I want you to see, well, I'll draw it in a second. What I want you to see right here from the center to the edge of the circle, what do we call that? We call that the radius. So we just found out our radius. Our radius is 4. So now if you wanted to, you could stop there and just plug it into the formula and say, oh, okay, well, 4 squared. Everybody's going to accidentally put 4. Sometimes that happens. Remember, the formula is equal to the radius squared. So this case would be 16. So 2 would be our answer for number 20. But in case you wanted to just draw it out, because sometimes they'll ask you to draw the actual circle, we go 4 up, 4 right, and 4 down. And try not to make fun of this circle. Let's see what we get. Hey, it autocorrects. Nice. So there's our circle. All right. So first things first, you have to remember this formula. I use H and K because that's how it was taught to me over 15 years ago. So I think it stayed the same. But HK is the center, R is your radius, and it's just equal to R squared, the entire thing. And that's the standard form of a circle. So you have to know that formula. It's going to pop up either like this, or they'll give you, the center, and they'll give you maybe a point on the line, and you have to figure out the distance. That's using your distance formula, that super fun formula between 2 points, and that'll give you the radius. All right. But it all starts with this. Got to be comfortable with that formula because it might not be multiple choice. It might be, you have to write it out yourself. Okay. And do not forget the double negatives. They get everybody. Okay. But that's pretty much it for this one. This is actually a pretty good worded problem. This is something that you might see on the SAT or the ACT. So this caught me by surprise. So if we look at this, this is super important. All right, so I'm going to give you something that you've learned already, but you might have forgotten because it's one of those like weird niche kind of formulas, or I guess it's a formula. But basically, in a right triangle, what I'm going to write is this: sine of A is equal to sine of B, and I have to type this out because I can't write all this much. Sine of A is equal to, no, not sine of B. Let's try that again. Sine of A is equal to cosine of B. Some of you might have caught that already, sorry. Cosine of B, if, and only if A and B are complementary. You can probably hear me typing, sorry. Complementary, and hopefully y'all remember what that is. That means that they sum to 90. If we add them up, they add to 90 degrees, okay? So what they're asking us here, in a right triangle, that's the important part. So if I draw this out and say, all right, we got a right triangle-ish, there's 90 degrees. We'll call this angle A, and we'll call this angle B. If that's the case, that's an A. That's the case. If this is true, that means that whatever this is and whatever this expression is, if I add them together, I get what? I get 90. And so what they want us to find out is, okay, well, what's the measure of the smaller angle? So that's all we have to do here. Using this formula right here, we know that A and B are adding up to 90. So whatever this is, in this case, A is 4x. Whoops, let's try and go down a bit. A is equal to 4x. B is equal to 3x plus 13. Plus 13 equals 90. So we just do a little bit of algebra here. So add the x's together. I'm going to subtract the 13. And we get, what, 77? And then we solve for x. We get 11. So now, if you look, it's like, oh, it's 1. No, that's just what x equals. A lot of people are going to put 11 because just to get to this point, like I know I'm going through this like, oh, it's really easy, but it's going to take a while. Like, you're going to go through some work just to get to this point. Be like, oh, wait. Yeah, oh, yeah, sine and cosine are equal, in a right triangle if, the two angles are complementary. So you got to add up to 90. And by that time, you might be tired and be like, all right, 11's a choice. Let me pick that. But that's not the angle measure. One of the angle measures is 4 times x. So 4 times 11. The other one is 3 times x, which again is 11 plus 13. We want to know what's the smaller angle. So again, we do a little bit of math here. What is that? 33 plus 13, 46. And if you look, which one's smaller? 44. And then just to double check, if you want, we can say, all right, well, we were operating on the premise that these two angles are complementary. If we add them up, they better equal 90 or something's up. Luckily, we add them up, they equal 90. And that's all we do for this one. Okay, so the main thing I want you to take away is this sine and cosine are only going to ever be equal if A and B add up to 90 degrees. Okay, when we're talking about acute angles anyway. Okay, so that's the big takeaway I want you to take from this, and then make sure you know what you're looking for. So we're looking for the angle measure, not just the variable. Like you remember from algebra, it's like, hey, I got the variable, I'm done. No, we need to take that variable, go back and plug it in, and then that gives us the angle measures themselves. We want the smaller of the two. All right, and that's pretty much it for this one. All right, a little more rotations and fun stuff. So basically, we want to know what quadrant is R double prime, basically the image of R. Basically, after we do some stuff to R, move it around a little bit, what quadrant is it going to be in? Okay, so we're looking specifically at R and saying, all right, 90-degree clockwise rotation. I'll show you a quick trick for that. followed by reflection over the x-axis. All right. So what I want you to imagine is, and it's really important that you know that we're doing the rotation about the origin. Okay. So what I like to do, honestly, just to check and see if my rotation is correct, is wherever I'm rotating it, if it's clockwise, so we're going this way, if I draw to where it's going to be, two lines to where from the origin to the point R, and then from the origin to where the image is going to be, that should be 90 degrees between those two lines that I just drew. So R is going to be roughly down here somewhere. Okay. Now, if you saw in the earlier question, it's really good if you memorize what the rotation formulas are. It makes life a lot easier. But if you just kind of need to know, like, okay, well, where, roughly where's it going to be at, this can help. But again, I can't stress enough, you need to memorize those formulas for, x becomes negative x, or in this case, x and y might swap and one of them becomes negative. All those rules. There's only a few of them, maybe 2 or 3, that if you remember those, you can, all of them. So super helpful to know those. You do need to know those, but you can kind of just get a gist of where it's going to be, at least using this technique that I like to use. If it was 180 degrees that we were rotating, we would go here, and then R would be somewhere over here because that's 180, right? Anyway, got off track there for a second. So R prime is roughly down here, and now we take that and we're going to reflect it across the x-axis. Ironically, now we're back up here somewhere. It's a little bit higher this time, so it's roughly up there. R double prime. So quadrant 1. So I was thinking about this. Ironically, we start in quadrant 1, we end in quadrant 1. Don't be annoyed by that, or be like when you're taking the test, like, wait, how could it be in the same quadrant? Like, that happens. It does happen a lot. They try and trick you and think, oh, like, how could it be in the same quadrant? That can't happen. Perfectly fine. That definitely does happen. And that's all we do for this one. We just rotate it 90 degrees, flip it across the x-axis, and that's all we're doing for that. All right, so if you remember in question 16, we had one that was really similar to this, where we had a right triangle and we had an altitude that was being drawn inside of that triangle. If you ever have that happen, what it creates is 3 similar triangles. That's one thing I want you to remember. A right triangle with an altitude drawn inside of it creates what I like to obviously call small, medium, and large triangle. What I said in the previous problem that had this for myself, this helped me when I was doing this in geometry a long time ago, but I actually would draw the 3 triangles. So you see them, and because they're similar, we know that corresponding sides are proportional. So left, bottom, the hypotenuses, those are all proportional. We can set up fractions or proportions between those sides, because we know that because they're similar triangles, all the sides are proportional, all corresponding angles are congruent. All right. So what they're asking us here is, okay, well, which ratio is always equivalent to cosine of A? So I think the easiest thing to do is, well, let's figure out what cosine of A we can find. I see angle A here, and if you remember cosine, if if they still teach the SOHCAHTOA method, cosine is equal to adjacent divided by hypotenuse. That's something you definitely need to memorize. So I'll write that out. So we have adjacent over hypotenuse. Excuse me. So what we do here, we'll look at this first one here, as there's an A on the small triangle. So the cosine of this angle is equal to the adjacent side, which is this one down here. So AD over the hypotenuse, which is AB. Now if you look, and it could be opposite. You can switch the order of the letters, DA over BA and what have you. I don't see that as an option here, so it wouldn't be that. Perfectly fine. Now you see another A, like, oh, okay, look at this A. Let's take a look at that one. Adjacent for this, the larger triangle, is AB, and the hypotenuse of the larger triangle is AC. Okay, and again, you can switch the order of the letters. It could be BA over CA, or any ordering of those. I don't see that as an option either, but remember, these corresponding angles for these triangles are all congruent. So that means angle B, angle C, these are all congruent. But also down here, even though you only see 2 A's, this angle right here is congruent. Now I said B, CDB, what was it, CDB? That's not technically B. This would be another, I'll call it B prime, because it's not, this is angle B. B is actually this one right here. So I should have picked a different letter for that. But that is another triangle that has, or sorry, another angle that's congruent to angle A. So we need to account for that as well. So the cosine of that, because these are equal angles, sorry, congruent angles, their cosine is going to be congruent as well. So let's write that out. Adjacent is BD. BD, that's a B. BD over BC. And these are all equal to each other. And if you look, it looks like we have BD over BC. And that's what you do for these ones. Excuse me. The big takeaway, I teach this with everybody because I think it just makes it easier to read the particular problem. Now, in my case, I shouldn't have drawn a B here. That's not B. That's, I don't know, you can pick another letter. You can put B prime if you want. But I like to draw the three triangles that are the three similar triangles that are created when we have a right triangle with the median drawn through it, because that's what's created. And it just helps you visualize, you know, what are the corresponding sides, what are the congruent angles, and things like that. So, and then once you have that, then obviously, you know, you need to know what cosine is. Cosine is the adjacent side. In a right triangle, it's the adjacent side, that length, divided by the length of the hypotenuse. Okay, and then you have to memorize, okay, well, it's not only A. In this particular case, this angle is also congruent to angle A. And that comes from the idea that you know what similar triangles means. Corresponding angles are congruent. Corresponding sides are proportional. Okay. So a lot of fun stuff in this one, but mainly being comfortable with this, you know, what that altitude does in a right triangle, and then also knowing your trigonometric ratios, sine, cosine, and tangent. So SOHCAHTOA, if you haven't seen that, make sure you know what those ratios are, because you have to know, obviously, you have to know what those are. This is kind of an introductory that you learn in geometry, and then you take it a step further in pre-calc. So that'll be fun. But anyway, long story short, that's all we need for this one. All right, the last problem. So for this one, what we have, they make this look just really weird looking, but ironically, it's actually not too bad when you start to draw some stuff out. So we have this large triangle, and we have these points drawn in such a way that LM and ST, those two line segments, are parallel. That's going to be super important. Remember, I always tell you, if they tell you something's parallel, draw it on the figure if you have one. If they say something's congruent, draw that on the figure so you know what you have and you don't forget it, like I used to. So we know that RL is equal to 2, LS is equal to 6, LM is equal to 4, and we are looking for the length of ST. All right, we know it's x plus 2, but we want to know the actual length of that. So here's the big thing. Hopefully you tried this. Maybe you tried it and you're like, I have no idea, don't know. What I want you to see here is, because these are parallel lines, one, I want you to imagine this smaller triangle, RLM, and then look at the larger triangle, RST. You notice how they both share this angle in common? Well, keep that in mind. Because these lines are parallel, I can't draw that. Because those lines are parallel, imagine RT being the transversal cutting through those lines. If I can draw this correctly, let me get rid of maybe some stuff here. There we go, a little bit. If we draw this, and then maybe one more to extend this line. Okay, if you look, I want you to see if you can remember, that's not a good line. I want you to see if you can remember one of the rules from parallel lines that would apply to this angle and this angle when we talk about parallel lines with the transversal. If you thought corresponding angles, you are correct. That's what those are. This angle and this angle, because these are parallel lines, corresponding angles are congruent. So we know that those two lines, let me get rid of those transversals, make this a little bit prettier. But because those are parallel lines, this angle and this angle are congruent. So you and I already established that both triangles, the small and the large one, had R in common. Okay, so if I draw this, small triangle and then the larger triangle, that's bad. We draw that one. They share this one in common. Now we just proved that they share this other one in common. That's enough to prove that these two triangles are similar by the angle-angle similarity theorem. Okay, if you can prove two corresponding angles of two triangles are congruent, then those two angles are similar. If we know that they're similar, now we know that the corresponding sides are proportional. Okay, so if you look at this RL, it's 2. If you look at the corresponding side, a lot of people are going to say, oh, okay, well, the bigger triangle is 3 times because, 2 times 3 is 6. You have to look at the entire length. The entire length is 8. So the smaller side, the smaller triangle has the length of 2. The larger triangle of the corresponding side has a length of 8. Well, that's times 4. That's 4 times larger. So the bigger triangle, the corresponding sides are 4 times larger than the smaller. So we know that LM and ST are corresponding. Well, if you and I know that LM is 4, we just found out that to get to the bigger side, we have to multiply it by 4. So 4 times 4, we get 16. Now, if you notice, we don't even need the x plus 2. They throw that in there. I don't like how this is, but it's just a good, I guess, problem-solving strategy. They just throw some extra stuff that we don't need in there. Now, if they had asked us to solve for x, yeah, we'd need that. But we just want the length. That's all we care about. So the length is just 16. Okay, so the idea is, one, if you, again, as you've gone through geometry, you've probably seen the pattern. If you see multiple triangles, usually trying to find out that they're similar is, 80% of what you want to do, or 90%, something like that. And that's what we could do here. And that's why you need to know your parallel line properties, corresponding angles, alternate interior angles, same side interior angles, depending on how they call it. Sometimes it's same side, sometimes it's consecutive interior, all that fun stuff. You have to memorize that. It's going to be on the test. There's probably going to be multiple questions on it, and it's actually going to probably be on the SAT and the ACT. Okay, so parallel lines, remember there's a whole chapter devoted to it. So just make sure you know those ideas. Again, alternate interior, corresponding, because we wouldn't have been able to solve this if we didn't know that, unless you took a guess. So that's all we do for this one.